Okay. Yeah, I found this little projectile motion problem in the review exercises, actually. So this is in the review exercises, number 40, for chapter 12. And it's here's what it says. It says, okay, let's see, a baseball is hit from a height of 3.5 feet. So it's a paragraph. Rather than writing the paragraph, I might just draw the picture. It says the baseball is hit at a height of 3.5 feet. They said it was hit with an initial velocity of 120 feet per second and an angle of 30 degrees above the horizontal. Okay, so they're giving me the angle. I told you before, I like these questions when they ask for the angle, but this time they gave me this angle. They gave me this initial velocity of 120 feet per second. They gave me the angle. They gave me that initial height, and they want to know the maximum height reached by the baseball. They want to know maximum height, which may be a topic we haven't discussed that much. Do you know how to find maximum height? I mean, there's a concept about maximum height. Do you know what it is?
Probably like find the derivative equals 0.
The derivative equals 0. Good.
Yeah.
Now hang on. You're right. At maximum height,
yeah,
the derivative equals 0. But wait a minute. We are dealing with a vector valued function here, and it's got an x component and a y component. So when you said the derivative equals 0, I wonder what we mean by that. In fact, let's fill in this stuff here. So the x component, and I've got this thing memorized, but you don't have to have it memorized. I'll give you some formulas. The x component is, sorry, I screwed that up. It's v naught, it's 120 cosine 30 degrees times t. The y component is h, that original 3.5 feet, plus 120 sine 30 degrees times t, minus 16t squared, right? That's how we do it in feet per second. That's x and y. So when you said the derivative equals 0,
yeah,
well,
it's not really.
Well, what do you think? Because if I did a derivative, I'd have my x derivative and I'd have my y derivative.
Mm-hmm.
My derivative is my velocity. My velocity, so what you're kind of saying is when you're at maximum height, your velocity is 0. The derivative is the velocity. The velocity is 0. You're right, but you know what? You're going to have some x velocity. That x velocity is never 0. That x velocity is always just this number. So what's really 0 is the y velocity. I don't know. You said the derivative was 0. I wanted to pin it down to
which component?
The y component derivative is 0. Right. The velocity of the y component equals 0. Right. Right. Or the derivative of y equals 0. You're right. So I should be able to actually do that here. Let's just do that. So the velocity vector is it's got an x component that's 120 cosine of 30 degrees. Like I said, that's just some constant.
Yeah.
Because you take the derivative with respect to t. For y, you get 120 sine 30 degrees. That's that derivative. Minus 32t. Yeah, this is it. Right. You set this equal to 0. This equal to 0. And that's pretty easy. It turns out the sine of 30 is a half. So this is a 60. Minus 32t equals 0. Nothing to it, I guess. Right. Cool. 60 equals 32t. Divide by 32. T is 60 over 32. Whatever. 1 point something. 60 divided by 32. 1.875. Okay, cool. Now wait a minute. That's the time it takes to get there. That's the time it takes to get there. Now I want the actual height, I guess. Is that what they asked for?
Mm-hmm.
Find the maximum height reached by the baseball. Right.
Just plug in T. Y.
Good. Plug it in
Position.
Where?
The Y position.
The Y position.
Yeah.
Thank you. Good. Exactly. So the Y position is, you're right, the 3.5 plus the, that's a 60, by the way, times T minus 16 times that T squared. Yep, that's cool. So you find, yeah, when the Y velocity equals 0, that's the time, but then you got to plug that time into the Y position to get the actual height. That's interesting. X doesn't play a role in this at all.
No.
X has a role in the range, but X has nothing to do with this height and this gravity and all this. So, cool. So that's some number. Let's see what it is. Minus 16 times. All right, I'm getting 59.75.
Yep.
Okay, cool. Feet. All right, cool. That's maximum height. When the velocity of y equals 0, and then we need that height. We need that position. All right, cool. Well, anyway, that was nice. There was another question here, to the same problem. There was another question that said, determine whether this is going to clear an 8-foot high fence that's located 375 feet from home plate. So that's a good question. So apparently out here, there's an 8-foot tall fence. And it's 375 feet from home plate. So X is 375 and Y is 8 out here. And we want to see if it clears it. Let's see here. So I like this question. Usually I'm asking, again, usually and I did this one the other day, I'm asking for the angle that lets it be a home run. I'm asking you for the angle that makes it clear the fence.
Yeah.
At this place, it clears the fence. And what this is saying is when X is 375, Y better be 8 or more, actually. But they gave us the angle, so there's nothing to, we just got to see if this, if this trajectory works. So again, I think maybe what I want to do is, maybe I should set my X, this is my X position, my 120 cosine 30 degrees times T, set that equal to the 375. Now what'll that do? I guess I'll find the time it takes to get there. The time it takes to get there. Let's just do that. It turns out the cosine of 30 is the square root of 3 over 2, so that's 60 square roots of 3 is what that is. 6 square root of 2, right. Times T equals this. Well, anyway, I still want to decimalize this. So that's 375 over 60 square roots of 3. If we make it a decimal, what is this? The time it takes to get to that distance. 375 divided by, I need parentheses, 60 square roots of 3.
3.61?
Yes, 3.61 seconds. Okay, cool. All right. So that's the time it takes to get there. Now, is it a home run? Or, I guess the question is, what is its height again? At this time, let's find its height. Maybe, I think the question is, as long as it's more than 8 feet, then yes, it's a home run. Right. So this is just a little different. I don't know if I've asked one like this, but now that we know the time it takes, we should plug it in and see what Y is. Again, let's find our Y position. The initial 3.5 feet plus that number is a 60 right there, times my time, and then minus the 16 times 3.61 squared. So at this moment, what is the y? That's a good question.
11.58. So yeah.
Okay, cool. 11.6 feet. All right, that's all I needed.
Yep.
It clears the 8-foot fence, barely. So cool. Yes, it's a home run. Yes. Cool. Yeah, that was a good question. Let's do another one. Let's do, right below it is 41. 41 says this, another projectile motion. Let's do another one of these. 41 says, a projectile is fired from ground level at an angle of 20 degrees with the horizontal. The projectile has a range of 95 meters. Find the minimum initial velocity. Okay, there's a couple of twists here, but it's fired from ground level. We don't know the initial velocity. That's what we're looking for. They did tell me the angle is 20 degrees. And there it goes. They also said it has a range of 95 meters. So it lands at 95 meters. By the way, all of a sudden, since they're using meters, it's up to me to realize that my equation is just a little different now. You know, my equation is always, for these projectile motions, you get to have this equation, but it's V naught cos theta t, comma, h plus V naught sine theta t. And then I always put minus 16t squared, but that 16 is half of gravity when we're dealing with gravity in feet per second. And this is in meters, so I'm going to use, not going to use 16, I'm going to use 4.9 t squared. Yep. Cool. And what am I going to do? I'm looking for V naught. I know that x is 95. I also know something else. When x is 95, what's y?
0.
Yeah, that's a true fact. And the original h is 0, by the way. But let me just see what I can say here. So x is going to be 95. Okay, so x is 95. I don't know V naught. I do know it's the cosine of 20 degrees, but I don't know the time. Right, so I don't know the time, I don't know the V naught, but I do know the angle. But x is 95. But that's two variables, so I can't go anywhere with two variables. I need another equation. And I guess we just said it a second ago. We said that when it does land at 95, the y position is 0. Okay. The y position is 0. Also, that h is 0. And then here we go. V naught sine of 20 degrees, an unknown t, and minus 4.9 t squared. Well then, maybe I should be able to solve for the V naught and the t and the V naught and the t. I guess I'll maybe solve this for t. T is 95 over V naught cos 20. That's my time. Take that time, plug it in here, plug it in here. I'll move over here where I got a little room. So then I'll have 0 equals, okay, V naught sine of 20 times t. And my t is this, 95 over V naught cosine 20. Yeah, that's interesting. Those V naughts are going to cancel out. Minus the 4.9 times the t squared, and that's that t squared. 95 over the V naught cosine of 20 squared. Cool. I'm going to do a little work here. You're right. The V naughts cancel. I could call that the tangent of 20 times 95, which is a number. let's just see what that is. I gotta make sure I'm in degree mode here. And tangent of 20 times 95. I'm making that a number. 34.58. That's that number. And then this is, excuse me, this is, I'm going to do this. I'm going to do 95 divided by cos 20. After I do that, I'm going to square it. And then I'm going to multiply by 4.9. 95, hang on, what did I say? 95 divided by cos 20. That's 101. I'm going to square that. I'm going to multiply by 4.9. And that gives me this big number, 50080.84. But it's all over this thing, squared. All over V naught squared. Did you follow that?
Yeah.
Okay, cool. Cool. So now we gotta just solve for V naught, which means, let's see, I'm gonna add this to the other side. If I add it to the other side, it's here. It equals 34.58. Oh yeah. So now I multiply this and divide by this. Right. So that thing divided by 34.58 is a 1448.26, and that's my V naught squared. So you're right. Take the square root. This is awesome. 38.06.
Yep.
Meters per second, I guess. That's my V naught. That's the V naught necessary to do what they said. What did they say? Oh, to have a range of 95 meters. I need that V naught. Cool. At that angle. Right. Given that angle, what's the V naught to get that far? That's cool. We can. Yeah, that's cool. All right. I like these problems. For some more good ones here. Let's see, we're about on this take-home quiz. The take-home quiz isn't too bad, maybe. But then there's some practice stuff on the back that's kind of rough.
Haven't done any of those yet, so.
Yeah. Oh, actually, there's a number 7 on the practice. It looks a lot like what we just did. That's cool. There is this proof here. It says, prove that the curvature of a circle of radius r is, I mean, we've said that, but I haven't really proved it. That if you have one thing we said is if you have a straight line, what's the curvature is? 0. And then if you have a circle with a radius of r, the curvature is 1 over r. That's true. I mean, yeah. So prove that, they say. Okay, great. And what my practice problem says, it says prove it 2 ways. I mean, first of all, if I have a circle of radius r, I could think of it as like back in good old rectangular equations. That's a circle centered at the origin, radius r. Now, if I solve for y, it gets a little nasty. It turns into, you move the x squared over, you take the square root, you get plus and minus the square root of capital R squared minus x squared. So that's y. And if I wanted, I mean, that's my circle of radius r, solved for y. I mean, I'm thinking about doing this formula. To prove his curvature, I'm thinking about doing this curvature formula, which is when I have a function of y, when I have just y as a function of x, the curvature formula was this absolute value of y double prime. Again, you don't have to memorize it, I give it to you. 1 plus y prime squared all to the 3 halves. Wow. So I'm thinking of using that formula with this function. I mean, that should be finding the curvature of a circle. This is a circle. This is it. This is the circle sort of written as a function. So it's got this nasty plus and minus. Yeah, so I'm thinking of doing that formula with this circle, with this function. So with this y. So that means I need y prime and y double prime, which gets a little rough. Okay, here, let's try it. What's y prime? Y prime is, I'm just going to leave the plus and minus here. You know, it's all this stuff to the 1/2. So you know how to do 1/2 times all this stuff to the negative 1/2. Times the derivative inside with respect to x. This is a constant. It goes to 0. And the derivative inside is a negative 2x. Wow. So this is my y prime. Let me just clean it up just a little. I'm going to cancel the 2 with the 2. Well, here's what's funny. You know, I got a plus and minus symbol out here. And then I got a minus sign. So the minus sign is just going to make the plus and minus a minus or plus. So I'm just going to lose the minus sign into the plus and minus. But I'm going to leave the plus and minus there. But they kind of, I'm saying that it sort of absorbs the negative sign. I got this x sitting here, and then it's, well, hang on, I'm going to call it x, and then it's times this thing, r squared minus x squared to the negative 1/2. R squared minus x squared to the negative 1/2. I just tried to clean it up a little because now I want to do the second derivative. I need to. I guess I need to do the second derivative. Okay, the second derivative though is a little product rule. Again, let's just keep the plus and minus out front, but now I'm doing a product rule, which is the derivative of the x. Okay, that's a 1. All right, cool. Write down the second thing. Okay, write down the second thing. Doing a product rule. Plus, write down the x. Okay. And take the derivative of this second thing. All right, well, that's a negative 1/2, parentheses, r squared minus x squared to the negative 3/2 when you subtract 1, right? And then the derivative inside is another negative 2x. All right, well, there it is. I'm going to move over here and I'm going to try to remind you how we used to clean these things up. One way we would clean them up by factoring out the r squared minus x squared. Here it is to the negative 1/2. Here it is to the negative 3/2. We used to do this thing where we would factor out the r squared minus x squared. We would factor out the lowest one, which would be this one, to the negative 3/2. So I'm pulling it all the way out. I'm kind of coming over here. The plus and minus is out here. The r squared minus x squared to the negative 3/2 is out here. Now what the heck is left? Well, when you factor in r squared minus x squared to the negative 3/2, out of r squared minus x squared to the negative 1/2, you're left with, do you remember? You're left with r squared minus x squared to the first. It's to the first, because if you multiplied it back, you would add exponents and you would get that.
Okay.
Plus, what else is left over there? Well, this whole thing is factored out. Hey, that 2 cancels with that 2. The negative signs cancel. What's left over there is a positive x squared. Oh my God. Which cancels with this x squared. So here's my second derivative, all cleaned up. The second derivative is this r squared with a plus and minus in front of it times this thing. Wow, that's my second derivative cleaned up. Here was my first derivative cleaned up. Oh my God, what am I trying to do? I'm trying to do this curvature. So I needed those 2 derivatives. They were a little nasty. Now I want to do this curvature, which looks nasty. Let's see what happens. Remember what it's supposed to be, though. What is this curvature supposed to be? For a circle of radius r?
1 over r.
Yeah. Okay, supposedly when I plug all this crap in, that's what I'm going to get. Let's see what happens. All right, I need the absolute value of y double prime. All right, here's what I'm going to do. I think the absolute value is just going to kill the plus and minus, basically. And so I'm just going to, the absolute value, put the absolute value on there, but then it's going to absorb the plus and minus. And I think I can just write this without absolute value. R squared times r squared minus x squared to the negative 3/2. That's my y double prime. The absolute value killed the plus and minus symbol. All over 1 plus this derivative squared. All right, that's this derivative. Squared. When you square the plus and minus, it's going to be plus. So I'm going to ignore that again. I'm squaring that x, so that's an x squared. And I'm squaring this, which is going to be r squared minus x squared to the negative 1. R squared minus x squared to the negative 1. I just took my derivative and squared it. All that is to the 3/2. Well, this proof wasn't as fun as I thought. We're getting there though. Here we go. All right, so finally, I think I'm gonna rewrite my numerator as an r squared over r squared minus x squared to the 3/2, but I don't know how much that helped. But maybe I'm sick of this negative exponent, so I did that. This denominator is 1 plus this x squared over, I'm going to write this over r squared minus x squared to the first. And then it's all to the 3/2. Well, okay. I think what I need is a common denominator between this and this. What is the common denominator of these 2 dudes? R squared minus x squared, which means I have to multiply him by an r squared minus x squared over an r squared. I mean, that's what that 1 is. It's r squared minus x squared over r squared minus x squared. When I add it to this, those x squareds cancel. Holy crap, what's going on, man? So then I get r squared over my common denominator, and it's all to the 3/2, which means he's to the 3/2 and he's to the 3/2. Did you follow that? When I got my common denominator, these x squareds eliminated, and I'm left with r squared over this common denominator, all to the 3/2, which means he's to the 3/2 and he's to the 3/2. What about this numerator? This numerator is an r squared over r squared minus x squared to the 3/2. When you flip this up, when you flip it up, he's in the numerator, r squared minus x squared to the 3/2. He's in the denominator, and you know what he is? He's an r squared to the 3/2. So he's wait a minute. So he's the square root of r squared, which is an r cubed. He's an r cubed.
And then it's just those cancel out. And then
those cancel out. R squared over r cubed is
1 over r.
1 over r. Wow. Okay. That was awesome. Or not. but it was a proof. We started with a generic circle of radius r. See, I didn't want to do it for, I mean, if I would have done it with, right, if r was 3, I could have done it with a 3. Anyway, the answer would have been 1/3. But that just proves it for r is 3. We did it for just any old generic r, and we proved that that's the curvature.
Using the original rectangular.
Using the rectangular
Okay.
coordinates, right? You're right. My practice piece of paper says do it using that. It also says to do it using a vector valued function. I don't think I want to do that one, but it might be worth trying. It's just a different way of doing it. All right. Well. We got a little shorter class today. Maybe we'll just call it a day now.
Okay.
We can find some other problems, but maybe we'll just quit today. So test Friday, unless the hurricane comes,
All right.
will get postponed till